You are welcome to chemistry class with your teacher and Christopher GK. In this particular video, today's class, we are going to look at the topic isotopy. This should be the topic of this particular class, and by the end of the class, you should be able to learn to define isotopy. Number two, you should be able to give examples of isotopes of some elements, then solve problems pertaining to isotopes. All right, let's look at them one after the other and go through the class. Please pay an attention as we look at the topic isotopy. Now, what is an isotopy? An isotopy is a phenomenon whereby atoms of an element is a bit different mass number, but have the same atomic number. When an element have the same atomic number, but different mass number, the phenomenon is what we call isotopy. So the mass spectrometer is an instrument that was used or is being used for the study of this particular thing to determine a substance that is isotopic. So mass spectrometric studies show that the atoms of most elements exhibit in more than one form. The study from mass spectrometer has shown that the atoms of most elements exhibit more than one form. And what does it mean? And how does it come about? It is because of difference in the number of neutrons present in these atoms. Is the differences in the number of neutrons of those atoms that resulted to it. And if that occurs, such atoms are said to be isotopes. Assuming now that carbon we know normally have 12 protons. Now, if it's inside it, carbon is 12, we have 12 proton, maybe neutron now is 12, and another carbon, we see another carbon with 13 neutrons. It's a problem. So the existence of such thing is what we call isotopy. Such phenomenon is what we call isotopy. When it have different mass number, because every element has already been assigned a particular mass number for it. When we now have a different mass number other than what is being known for, but the same atomic number that it has been, is an issue of isotopy. We call the phenomenon or such thing isotopy. Now, isotope of an element is represented by the original symbol of that particular element with the mass number and atomic number being given to it. As an example, as I said before, carbon, we know is carbon 12. The mass number of carbon is 12. Atomic number is 6 because it's the sixth element in the periodic table. If we have now that the mass number of it, which has been known, which has been determined by mass spectrometer as an instrument, if we have 2 carbons and one is 12, we have one, we examine it and one is 12. And another one, we have it as 13. Another one, we have it as 14. All of them still have 6 electrons or 6 protons. It's an issue, and that is what we mean by isotopes. It's an idea, are isotopes of carbon existing with the same atomic number but different mass number. So in such a case, this particular example, carbon 12, carbon 13, carbon 14 represent atoms of isotopes of carbon. So isotope 12, isotope 13, isotope 14. For each atom, the number of the neutrons can be represented by filling the differences, or finding the differences between the mass number and the atomic number, which is A minus Z. A is the mass number, Z is the atomic number. When you do that, you're going to find the number of neutrons, and you observe that the first one, the number of neutrons there is what? Is 6. The second one, the number of neutrons there is what? 7. The number of neutrons in the last one is 8. This is an issue of isotopy. And the three of them are isotopes of carbon. That is an example. Each isotope of an element has its own mass number as isotopic mass. That actually is not the mass of carbon. The mass of carbon is 12, generally known. But existence of it in this form is what we call isotopy. And there are different mass now is what we call isotopic mass. Okay? Now, isotopes of an element have slightly different physical properties because neutrons contribute only to the mass of an atom and not its chemical behavior. The only difference now is their physical behavior will be slightly different, but issue of their chemical behavior, it will be the same because neutrons contribute only to the physical behavior of those elements involved. So isotopes of an element exhibit the same chemical properties because the number of valence electrons in an atom of an element determines its chemical behavior or chemical properties. And since isotopes have the same number of valence electrons, they will be chemically alike. They will be chemically the same. So different isotopes of a particular element does not alter their chemical behavior, does not alter their chemical character, but their physical behavior or physical properties is what will be slightly different. Hope you are following. So isotope mass number of 12, mass number of 13, mass number of 14 of that of the carbon is only slightly different in their physical behavior, but chemical behavior, they are the same. That is what isotope does because neutrons only affect the physical behavior, the inside the nucleus of an atom. Okay, now let's take a look at this. An analysis of chlorine isotopes, we observe that here we have chlorine 35 and chlorine 37. On it, of course, our usual atomic number is the one below, which is 17, the atomic number of chlorine. Then chlorine 35, chlorine 37, the atomic number there, mass number is 7. Atomic number, sorry, mass number is A, which is 37 and 35. Atomic number Z, which is 17, is the same. Still remember the definition, the same mass number, atomic number, but different mass number. Now the number of proton is the same thing to the number of, is the same thing with the atomic number, and also the same with number of electrons. But where the issue is the number of neutrons. How can we determine that? Mass number minus atomic number or proton number. It gives you the neutron number. And when you do that, you are going to have that chlorine 35. You are going to have 18 as the number of neutron present there. But that of the chlorine 37, we are going to have the number of neutron there as 20, which is unusual. If you use this value to calculate for their percentage in a percentage abundance in measure, you are going to have that chlorine 35 has 75%, while the chlorine 37 has 25%. Of course, you know that the real atomic mass of chlorine is 35.5. So the chlorine 35 is the one that is more abundant than chlorine 37. So that is it as an example of isotope. So we have already seen that carbon has an isotope, isotope 12, carbon 12, carbon 13, carbon 14. Chlorine is another example. Chlorine 35 and chlorine 37 is another example of isotopes. So isotopes of some other elements aside this one we have said now. Of course, carbon, we have said carbon before. you can see oxygen. We have oxygen, 16 oxygen, mass number 16, 17, and 18. When you look at it, the abundance of carbon 12 is 98.9. Of course, carbon, we know carbon as carbon 12 as the mass number. That is why the abundance is high, the percentage abundance. Then that of the 13 is 1.1. You see, it's very, very minimal and it's not been, it doesn't occur regularly. It shows that the abundance is very, very minimal. Now, in that of the oxygen, abundance of that of the percentage of oxygen 16, mass number of 16 is 99.76. Of course, oxygen, we know the relative atomic mass as 16. That is why it is more abundant. That of 17 is 0.04. That of 18 is 0.20. You see, they are not in abundance like that of the first one. We have other, that is number 3 examples that we have cited now. We have other examples like hydrogen. It also is a bit isotope. So the isotopic forms of hydrogen are protons, that is proton, which is normal hydrogen, neutron, and triton. Triton now is when hydrogen has relative atomic mass of 3. Neutron is when it has 2, which is heavy hydrogen. We normally use D to represent it. Triton, we use T, capital T, to represent it. But normal proton is the hydrogen normal 1,1, atomic mass 1, relative atomic number 1, atomic mass 1. That is it. So we have given you at least 4 examples of isotopic elements. We still have others, but let's move into how to get calculation done on this. Maybe if you want to calculate the abundance of it, or to calculate the relative atomic mass, or the particular atomic number of the such elements. Now let's look at some worked example. We are asked to determine the relative atomic mass of element X from the data below. A compound, an element that is a bit isotope of 24, 25, 26 has mass. It means that the mass of relative atomic mass of such element is 24, 25, and 26. And the abundance of them are just 78.70, 10.13, and 11.17%. That is the abundance of those masses of such elements in nature. We are asked to calculate the relative atomic mass of such particular element, of element X. Now, what should we do? We are going to multiply each mass with the abundance and divide it by 100 and get the value. All right, the first one, we have the abundance as what? 24, the mass as 24, the abundance 78.7. So 24 times 78.7 plus 25.10.13 times 26 times 11.17 all over 100, because we are calculating is percentage, they are in percentage, equal to X. You are looking for the element X. When you sum it together and divide it by 100, you are going to have the summation as 2,432.47 divided by 100 equal to X. X now will be 24.3247, approximately 24. If that is the case, of course, in our periodic table or relative atomic mass, we have an element that has 24 as the relative atomic mass, and that is why 24 here has the highest abundance in nature in this isotope. So that is it, how to calculate for the relative atomic mass of that. Now let's take another example. An element S has 2 isotopes of 20 and 22. Element X, which is atomic mass, atomic number is 10, then the atomic mass is 20 and 22. In the ratio of 2:3. What is the relative atomic mass of such elements? that has 20 and 22. What we do, first thing is to add together their ratios. The occurrence together, add it in ratio of 2:3, 1:3. 1 plus 3 is going to give it, it will give you 4. So from here, we observe that the abundance, that one that of 20, a mass number of 20, is in abundance. The ratio is 1. That means 2 times 1, 20 times 1, plus the other one that is 22, 22 times 3, all over their common ratio, which is 4, equal to S. Add it together, 20 plus 66 divided by 4. And when you divide, you're going to have 21.5. That is the relative atomic mass of such elements. Of course, in the periodic table, of course, neon is number 10. Is number 10, and the relative atomic mass of it is what we have here. The other one we studied, we had 24, and it's also an element in the periodic table. So this is how to calculate this one. Can we look at the other one? Let's also see how it can be calculated. This question says, isotope of an element X have isotopic masses 65 and 63 respectively. That the masses of that element isotope of X are 65 and 63. If the relative atomic mass of X is 63.60, find the relative abundance. Now, the relative abundance, the percentage of each isotope of the element. Now, this one need to be practical about it and follow it sequentially. Now, look at how can we get that form solved. First thing we need to do is just to assign letters to those elements, to the isotopes of X, in order to give us opportunity to solve this with an equation. What we are going to do is this. Let the relative abundance of X, of element X, be Y and Z. We don't know it. So, but we know that abundance is in percentage. It's in percentage abundance. That means it's 100. Meaning that Z plus Y should be equal to 100. Now, Z, making Z or Y, any of them, you can make any of them the subject of formula in order to enable you to solve it. Z now will not be 100 minus 100 minus Z minus Y will give you that of the equation for Z. If you want to use Y, you are going to be Y equal to 100 minus Z, whichever one you want to use. After that, what else we will do now is this. 65 there is for Y. Then you can use any one, 65 or first one, or assign the other one as a Z, only that choose them. So 65 times Y plus 63 plus Z. Look at the question, 65 and 63. Y comes first before YZ. So we choose Y as 65 and Z as 63, equal to 63.60, which is the relative atomic mass of the element X given in the equation. All of them divided by 100. So 63 times Y plus 63 times Z all over 100 equal to, all together should give you 63.60 according to the question given to you. The next step now is to open this particular bracket, multiply through and open the bracket by cross multiplying 100 times that's 63.60. If you do that, you're going to have 65Y plus 63Z equal to 63.60 times 100. That's 0. That 100 beneath, you will use it to multiply the other one at the other side. And when you do so, collect like terms. When you collect like terms, you are going to have 65 plus 63. Now, in equation number 2, equation 2 there now is that 63Z. But in equation 1, we make we found the value of Z. We made Z the Soviet formula, which is Z equal to 100 minus Y. So substitute it into that equation 2, substitute it there so that we will have only one unknown in order to find a value for Y. If you substitute it, 63 close in bracket 100 minus Y. When you now open the bracket, use 63 times Y and 63 times 100. You are going to, when you open the bracket, you have, when like terms are being collected, 65Y minus 63Y plus 6,300, which is 63 times 100, equal to 6,360, which is normally at the right hand side of the equation. Collect like terms. When you minus, you're going to have only 2Y equal to 60. Make Y the subject of formula. You're going to have 30 and 30. What it means that abundance of Y is 30. Using this as a value of Y, bring down the equation once again. Z equal to 100, which is in the equation 1 we have here. Z equal to 100 minus Z minus Y. Bring it down. And when you substitute, Y now is 30. Substitute, you're going to have Z as percentage of 70. By that implication, what we have succeeded in having now is that percentage abundance of Y is 30, percentage abundance of Z is 70. Altogether, we have found out that relative abundance of X is 30 of that particular element given to us. 30% of X, which is 65, and that of 70% of X, 63 isotope of relative atomic mass of 63. So that is what we have done. And it's wonderful. And that is how to calculate the isotope relative atomic mass and relative atomic number or relative abundance. Okay, the relative atomic mass is based on carbon-12 isotope. Now, the relative atomic mass of an element is the number of times the average mass of an atom of an element is heavier than 1/12 of the mass of one atom of carbon-12. So we are using carbon-12 as the basis. We use it as the basis to determine the relative atomic mass of other elements. Now, relative atomic mass, which is RAM, relative atomic mass in abbreviation of an element, can be defined this way. Average mass of one atom, of a particular atom of X is, that means divided by 1/12 mass of one atom of carbon-12. You can define this way and it's still very, very acceptable in whichever way. Thus, the atom of carbon-12 is adopted as the standard for defining the relative atomic mass of an atom of other elements, and is being given as a basic mass volume of 12 units. So as I said before, we use carbon-12 as the yardstick, as the basis of defining other elements in the periodic table. So it's the number of times such particular average mass of an atom of an element is heavier than 1/12 of the mass of one atom of carbon-12. All right. The relative atomic mass of each element has been determined accurately with the aid of the mass spectrometer. I said it in our last video. We use mass spectrometer to determine the relative atomic mass of elements. This instrument measures the masses of the isotopes of the elements and the abundance, and the relative atomic mass is calculated from the data. So we use it to determine the relative atomic mass of elements and even the relative abundance of those elements of the isotopes in the elements. So we use it to determine the isotope of elements and their relative abundance, their relative atomic masses. So that is what the instrument mass spectrometer, that is what it does. All right, look at the relative atomic masses of elements. It has been determined. What you just need to know is to look at them, learn them the way you learn your atomic number of first 20 elements. At least the first 20 elements, you are to learn this one. The relative atomic masses of the first 20 elements in the periodic table. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium, which is number 20. Just know them, cram them, possibly if it is cramming you need to do, but of course, as you look at it critically, you will learn them and have them offhand. So these are just the relative atomic masses. It has been done, it was determined using mass spectrometer. That is it. So far, we have talked about issue of isotopy. Isotopy is a phenomenon, but those elements, those atoms that does it, those examples are the isotopes of such particular element. But the phenomenon, isotopy is just a phenomenon, the existence. It's a phenomenon whereby atoms of the same element, of atom of an element, is a bit different mass number, but having the same atomic number. We call it isotopy. We call it isotopy. This is due to the difference in the number of neutrons present in these atoms. It's the number of neutrons in this element that determines the isotopes. Such atoms are known as isotopes. Isotopes of carbon, isotopes of oxygen, isotopes of hydrogen, isotopes of chlorine, and the others. Isotopes of an element have slightly different physical properties, but it's a bit same chemical properties. There is a bit same chemical properties, and that is what we have done so far. All right, for further discussion and inquiry, make sure that you get to me. Get back to me, contact me, and through my phone line 080 or +234 80 655 73229 +234 80 655 732. That is my phone line or my WhatsApp line. Or you can send me an email with my email address, through my email address at Cristo, CAKRISTO116 @gmail.com. Cristo is AKRISTO116 @gmail.com. Remember to give me feedback. Give me feedback. Contact me, give us comments on how the video, the area you like and what you don't like, or commendation and all of that. Give us feedback and like it. Thank you and be blessed for being part of this particular class. And get ready for the next video and next class.